So when we are talking of periodic table, okay, we begin with historically what happened in while we were finding out the periodic table. It is clear. So historically, how did the periodic table get formed? The first attempt at classifying, what was the need? Initially, when they knew only 2 or 3 elements, there was no problem. But slowly, as the number of elements got discovered was quite a bit, is this clear? Then the problem arose that they wanted to classify. So the first person who classified elements was Proust. Now, Proust classification is also called as unitary method. So what he said was that hydrogen atom is fundamental and other elements are formed by combination of hydrogen, atom. So it didn't take much time for people to simply call the bluff in this, that Proust. After Proust, what happened was, we had Daubigner's law of triads. See, what he said was that when elements having similar property, he said that when elements having similar property were arranged in the increasing order of atomic weights. The atomic weight, so he said the atomic weight of the middle element, what he said was the atomic weight of the middle element, the atomic weight of the middle element atomic weight of middle element is average of the first and last element. What he wanted to say was, suppose we have lithium, sodium, potassium. So lithium was atomic weight 9, this was something like 20. So he said 9 plus 20 is 29 divided by 2 is nearly about 2 ones are 2, and then potassium was atomic weight. Yeah, see, it was 7, I'm sorry, this was 7 and this was 23. So this will be approximately how much? 29, and potassium was 39. So this value became around 23, which was what was a fact. But then what was the problem? The problem was that very few elements in triads existed like this. So this did not apply for many elements. So this was not considered as an appropriate method. So after this was Newland's law of octaves, or Lothar-Meyer's. There can be a lot of questions asked on this. We have the Lothar-Meyer's graph of atomic volume. So what he did in Lothar-Meyer's graph of atomic volume was, he found out the atomic volume. How can you find out the atomic volume? It is atomic weight. It is atomic weight divided by density. So it is atomic weight divided by density. So what happened was, he drew a curve. So when he drew a curve, the conclusion of this curve are MCQs in the examination. So he drew a curve of atomic volume on the y-axis and atomic weight on the x-axis. So he realized the curve was something like this. So what he found was that alkali metals which had maximum atomic volume, so we can say somewhere here. So we have lithium, sodium, potassium, rubidium. So what was his observation? That alkali metals occupied the peak. Okay. Then we have lithium. So you can have over here, so this will be beryllium, magnesium, calcium, strontium. So what is this conclusion? That the alkaline earth metals, occupied the descending curve. Occupied the descending curve. Okay. Then he realized that halogens and inert gases. So you have fluorine, chlorine, bromine, or fluorine, chlorine, bromine. Okay. So bromine. So what can we say about this? The halogens and inert gases, halogen and inert gases were occupying the ascending part of the curve. Were occupying the ascending part of the curve. And here at the rock bottom, you had, because transition elements had the lowest atomic volume. Is this clear? Inner transition we'll see later, but then what Lothar-Meyer said was this, that since atomic volume of transition metal were lowest, so transition metals occupied the lower part of the curve. So this was one kind of classification. It has its own importance because it was much specific. Okay, but still the scientists found it very difficult actually to understand the properties of elements from the position in the curve. That was their main aim, that they wanted to understand the properties of elements from the curve. So then subsequent to this, what happened was, there was an attempt, or it was second, third, this is the fourth attempt, was Newland Newland law of octaves. So octave is the music scale. Do, re, mi, fa, sol, la, ti, do. Like we have in Indian classical music, we have sa, re, ga, ma, pa, da, ni, sa. Like that, in octave, in English music, we have octaves. Do, re, mi, fa, sol, la, ti, do. So what did he observe? He observed that if elements are arranged, if elements are arranged in the increasing order of their atomic weights, in the increasing order of their atomic weights, if they are in the increasing order of their atomic weight, the eighth element had properties similar to the first. Properties similar to the first. Had properties similar to the first. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluoride. So 1, 2, 3, 4, 5, 6, 7. The eighth element, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. So if we take beryllium, 1, 2, 3, 4, 5, 6, 7, 8. But then what was the problem? That this was only for this much limited elements this was working. It did not work in case of what? Transition elements. It did not work in case of transition elements. But there was some help that Newland gave to Mendeleev. Mendeleev's periodic law. So it started with Mendeleev proposing his Mendeleev periodic law. In Mendeleev's periodic law, he said that the chemical properties of elements are a periodic function of their atomic weight. So based on this, he produced a periodic table. In his periodic table, what happened was, he had divided this into, initially it was 8, and then it became 9. So he had 9 vertical columns and 7 horizontal rows. So we had group 1, 2, 3, 4, 5, 6, 7, 8 and 0 group. That was added later on. First only 8. And then we have 1, 2, 3, 4, 5, 6, 7 periods. Then what happened was, each of this was divided into A, B. Subgroups A, B, A, B, A, B, A, B, A, B, except 8 and 0. Now this was quite a what do you call effort that he had done, but there was only one problem, and I mean sometimes some elements having higher atomic weight were placed before, then he had to make the correction, arrange them according to their properties. Position of hydrogen was not clear, position of lanthanides and actinides was not clear. So for all the defaults in the Mendeleev's periodic table, it was still a very, very compact periodic table. It is clear. But then subsequently what happened was, they did an experiment. What he did was, he drew a graph of square root of frequency of X-rays versus atomic weight of metal. So what we carry forward from structure of atom. What did we learn in structure of atom? That when electrons bombard metals, they give out X-rays. And these X-rays will have different frequencies depending on the metal. So that's what Moseley did. He drew a graph of square root of the frequency versus atomic weight, and he got something like this. The graph was not proportional. But the moment he changed the condition, when he drew a graph of square root of frequency versus atomic number, the graph was like this. It was a linear graph, linear regression. We call this as linear regression. What do you mean by linear regression? There's a direct proportionality. There's a direct proportionality between the atomic number and the frequency of the X-rays which were produced by bombarding electrons on that particular metal. It was this experiment which made him realize that the property of an element is not a periodic function of atomic weight, but of atomic number. So therefore what happened? Moseley proposed. So Moseley only proposed, remember that. So Moseley proposed the modern periodic law. Modern periodic law. So according to Moseley, he said that the properties of elements are periodic function of their atomic numbers. Remember one thing, that he had just proposed the modern periodic law. He didn't what you call chart out the modern periodic table. This is something which our textbook missed actually. It was Bohr. Bohr is going to haunt us for a long time. It was Niels Bohr and his assistants, I tell you the names are tricky, Rang and Warner, along with Rang and Warner. They formed the modern periodic table. So this is a misconception that we have in our earlier years, that it was Moseley who made the modern periodic table. No. It was started by Bohr and then in 1984 it was changed a little bit. Because Mendeleev, these fellows also had taken 1A, 2A, 1A and 1B and 2B and all that. And then in 1984 IUPAC said, let us make it 1 to 18 vertical columns, were called as groups 1 to 18. That's the only change which happened. So they formed the modern periodic table. They formed the modern periodic table. So in the modern periodic table that we have now, what do we have? I will draw it over here. Elements of the third period, so we have groups. These are 18 groups. So period 1, 2, 3, 4, 5, 6, 7. So elements of the third period, but of the 6th and the 7th group, can you see over here? See, in one block, one such square, we are supposed to accommodate only one element. Is this point clear? But what happens? 14 elements, lanthanum to lutetium and actinium to lawrencium, that 103, they were having very similar property that they have to be accommodated only there. Otherwise the properties will get disturbed. So they were placed separately at the bottom of the periodic table. So these elements, these 14 elements, were placed separately at the bottom of the periodic table. And they were called as lanthanides and actinides. So this was from the 6th, this was from the 7th period. So this was the skeleton of modern periodic table. This is a skeleton of modern periodic table. Now let us talk about periods. So it has 7 periods. Is this point clear? So in the first period is called as the smallest period. The first period is called as the smallest period. Why are they called as smallest period? Because there are only 2 elements, hydrogen and helium over here. Hydrogen and helium. The next 2, the second and the third period, they are called small periods. Why are they called as small periods? Because they include 8 elements each. They include 8 elements each. So which are they? We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then we have neon. Okay. Here we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Now elements of the second period, they are called as elements of the third period. First let us know. They are called as representative elements. They are called as representative element. And elements of the second period, they are also called as bridge elements. Why are they called as bridge elements? Because they show what we call as diagonal relationship. So what happens is, what is diagonal relationship? Let us study over here, because that's a question on its own. Write a short note on diagonal relationship, and then every time when we study S block, P block and all that, similarity between these elements is also something which we have to study. So what is diagonal relationship? I'll show it separately. I'll write it here because So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. This is which period? The second period. And then we have third period. We have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. See, what happens is elements of the second period. See, in a group, suppose if I write the group, we have lithium, sodium, potassium, rubidium, cesium, francium. In a group, we have put them in a group because we expect that we are aware, not expect. We know that their properties are same. Why are their properties same? Their properties are same because of similar outer electronic configuration. So in a group, properties of elements are same is a natural phenomenon. But here what happens is, between elements of the second period, so what is diagonal relationship? Diagonal relationship is elements of the second period, elements of the second period show similarity with elements of the third period. Elements of third period, but of adjacent group. This is called as diagonal relationship. So what we have, lithium has some properties similar to beryllium. So it is like acting, these properties are acting like a bridge between two groups. That's why it's called as bridge elements. Why are they called as representative elements? That also we'll discuss. Elements of the third period is called, or are called, why is called? Are called representative elements. Why are they called as? Because they represent the group to which they belong. They represent the group to which they belong. So what does it mean that they represent the group to which they belong? That means, suppose if I take lithium, sodium, potassium, rubidium, cesium, francium. If I study the property of sodium, the properties of other elements in the group are somewhat close to that of sodium. Instead of studying property of each and every element, so 105 elements, if I had to teach you to properties of 105 elements, you will quit chemistry and run away. You have a chance still, it is clear. You are in 11th standard. But if I tell you, okay, instead of that we have to only study properties of 10 elements and the others 105 revolve around the properties of these 10, you will say, TK, once in a while we will take a chance, 10 elements we will study. So this is what I am trying to tell, that they represent the group to which they belong. So that is why even in the studies, they are taught us extraction of sodium, we are studying this, extraction of sodium, aluminium, silicon, phosphorus, these elements are taught because it is an understanding that if we are taught these elements, their properties, extraction methods, physical property, you will know the property of all the elements in the periodic table. It's a different thing that you don't know even this nor that, it is clear. But this is the assumption of the International Union for Pure and Applied Chemistry. Is this point clear? So this is about representative elements. Then let us look at further. We have the fourth and the fifth. The fourth and the fifth period, they are called as long periods. Why are they called as long periods? because they include 18 elements each. Then the sixth is the longest period because it includes 32 elements, including 14 of the lanthanides. Then the seventh period is an incomplete period. See, we are aware of about 20 elements. I am not writing down because while I say 20, some other fellow will say 21 because something was discovered. But actually there should be 32. Just like the earlier one, the sixth period, seventh period should also have had 32 elements, but elements beyond uranium. Is this clear? They are called as transuranic elements and they are not found in nature. They have very short half-life, they are radioactive. Is this clear? So they have been found artificially. So up to 105 lawrencium, everybody is very sure. So we said 20 elements approximately is known. Another 20 and 32 means 12 more elements have to be discovered. But so this is about what do you call the periods. Then when we come to the groups, so this was about period. Then we come to the groups. So what is a group? A vertical column in the periodic table. Vertical column in the periodic table is called group. Is called group. How many groups are there, you tell me? There are totally 18 groups. There are 18 groups numbering from 1 to 18. After 1984 I told you, otherwise we used to have 1A, 1B, 2A, 2B, 3A, 3B, just like Mendeleev's periodic table. But this was rationalized in 1984 by IUPAC. I was born in 1984, don't worry, I was born 1961. In fact, in our time, 1980, I am a 12th standard pass out of 1980. We used to have 1A, 1B, 2A, 2B. So 1A, what is 1 now here is 1A, and then we had this group 3. It used to be 1B and all that, you know, group 3B, 3B, 4B, 5B, 6B, 7B, 8, 1B and 2B. So that is how the numbering used to be. But in 84, they decided to rationalize 1 to 18. It became easy for us, for you people. Because by that time I had studied. So 18 groups, numbering from 1 to 18. Is this clear? So what do we have? Elements of group 1, they are called as alkali metals. Elements of group 1 are called as alkali metals. Why? How did we get the name alkali? It was from the Arabic word al-khali, which means ash, wood ash. Because they found that ash of wood was alkaline in nature, red litmus turning blue. So al-khali was, those days the Arab civilization and the Greek civilization was far more advanced than the European civilization. It is clear. Somehow along the way the Arabs lost their touch with science. It is clear. So they are remaining behind. Even today they are having their own problems. It is clear. They are not able to fight Israel. Is because they are technologically savvy, and Israelis are much more technologically savvy. But they were a civilization which was very, very knowledgeable. So group 1 is alkali metal. Group 2 are called as alkaline earth metals. Okay. Then what happens is, from group 3 to group 12, group 3 to group 12. They are called as transition metals. Transition elements. They are called as transition elements. Is this clear? Then we have group 16. I am only talking about those groups which I got a special name. Elements of group 16. So what are oxygen, sulfur, selenium, tellurium, polonium. Group 16 elements are called as chalcogens. Why are they called? This is a question which you can expect in the entrance exam. Why are they called as chalcogens? They are called as chalcogens because they are ore forming. If you see any of the ores are either oxide ores or sulfide ores. It is clear. Then group 17, they are called as halogens. They are called halogen. The name was derived from the Greek word hals, which means sea salt, and gens. Gens is genesis, obtained from. And then we have group 18. They are called as inert gases. So now you will ask me, sir, what about 13, 14, 15? They are simply called as elements of boron family, carbon family and nitrogen family. There is no special name for them. They are called as boron family from the name of the first element, boron family, carbon family and nitrogen family. Is this point clear? So now, what was the drawback of modern periodic table? So that we will look at it over here. The drawback of modern periodic table was I'll stop at this because I have to start next with classification based on electronic configuration. That takes about an hour. I don't think I have that much time, so I don't want to start a topic and leave it behind. Is it clear? The first and foremost drawback was position of hydrogen. Position of hydrogen. See, hydrogen could easily lose an electron to form H++ an electron, a property similar to that of alkali metals. But hydrogen also had the capability of accepting the electron to form H-. This is called as hydride ion. This is a property very similar to that of halogens. In fact, the ionization enthalpy, I am going to teach you what is ionization enthalpy in this chapter. The ion enthalpy of hydrogen was more closer to halogen than alkali metals. Alkali metals are supposed to have lower ionization enthalpy. Then the second problem was what? The position of. So what they did finally was they placed hydrogen at the center of the periodic table. Somewhere here. So that means your smallest period, helium, will have only one element. The first period will have only one element because they placed separately hydrogen here in the middle of the periodic table. So a solution was found for that. Then what do we have? Position of lanthanide and actinide. They were placed separately at the bottom of the periodic table. We wanted a periodic table where everything will be within that only, nothing separately on the side and inside, on the bottom of the periodic table and all that. That was of course a drawback. And lastly, third point was what? The modern periodic table modern periodic table gave no idea of what electronic configuration, especially the outer electronic, let us write down that, of outer electronic configuration. Why are we so keen on outer electronic configuration? Because the characteristic property of an element is because of its outer electronic configuration. Electronic concept of valency, that is the rule. The rule says that the chemical property of an element is because of its outer electronic configuration. So how did they overcome this problem? They overcame this problem by dividing the whole periodic table into 4 blocks: S block, P block, D block and F block. This is something which we look at